Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome back to the deep dive. If you work in industrial microbiology, I'm willing to bet most of your energy goes into the biology. You're wrestling with strain genetics, dialing in media recipes, agonizing over feed strategies.
That's the natural place to focus. We spend so much time on the life inside that giant stainless steel box.
Exactly. But today, we're going to force a crucial perspective shift based on the source material we've been reviewing.
Yeah, these articles argue that while the biology is obviously vital, it operates entirely within the boundaries set by the fermenter as an engineered system.
And if that system isn't perfectly ready, your biological results could be, well, meaningless, or at best, just randomly irreproducible.
That's the core idea. So our mission today is really a shortcut to understanding that one non-negotiable prerequisite for getting robust, scalable results.
What the sources are calling fermenter readiness. And just to be clear, we are not talking about a simple pre-run checklist. This isn't about, did you check the pressure or did you sign the logbook?
Not at all. The argument is that readiness must be treated as an engineered state. It has to be measurable, it has to be validated, and it has to be trended across entire campaigns.
Because the fermenter sterilization performance and its measurement integrity, that's what determines if the cell behavior you see today is what you'll see tomorrow.
Precisely. It's about imposing predictable and stable constraints. Without that, you're just guessing.
Okay, let's unpack that a bit. So you've followed your SOP, you've ticked all the boxes, pressure tested the system, everything looks fine. What does it even mean for a fermenter to be functionally unready?
It's a great question because functional unreadiness comes from what the source material calls latent uncertainties.
Latent uncertainties.
Yeah, these are the subtle flaws you just can't spot on a simple checklist. True readiness is the ability to impose stable, predictable constraints. If that constraint is unstable, your biology is basically starting on a moving target every single time.
Can you give me a tangible example?
Yep.
What kind of flaw is hiding in the background here?
Sure. Think about incomplete air removal during the sterilization cycle. You get these little air pockets that act as insulators.
Okay.
Or maybe uncharacterized condensate holdup pooling at a drain valve. Or a cold spot hiding behind a thick flange that you'd never see.
Or even just slow systemic sensor drift that started 3 campaigns ago but hasn't actually triggered an alarm yet.
Exactly. So the system hasn't catastrophically failed.
Yeah.
It's not gushing steam and you're not seeing immediate, obvious contamination.
Right. So how do these small latent issues actually show up in, multi-million-dollar production runs?
Well, that's what makes them so insidious. They rarely cause that immediate dramatic failure. Instead, they manifest as, say, suppressed productivity.
Or just unexplained run-to-run variability.
Exactly. Or a gradual erosion of the whole campaign's robustness. You think you're optimizing the strain, but really you're just optimizing the biology against these shifting starting conditions that are being driven by the equipment itself.
So the biologist is basically playing a game of darts, and the engineer keeps secretly moving the dartboard a millimeter every single run.
That's a perfect analogy. And it's a fundamental flaw in process control, which is why readiness needs a really rigorous framework.
It has to be demonstrated under conditions that emulate real use.
Right. And the source material defines this using 4 coupled pillars: sterile boundary integrity, SIP execution quality, instrumentation integrity, and then dynamic response reproducibility.
And a weak point in any one of those pillars immediately becomes what they call a biological confounder.
It does. Let's look at that enzyme production example from the sources. I think it makes the whole thing really tangible.
Okay.
So in this generic industrial system, the vessel passed a standard sterilization in place cycle. It was officially released for production.
Right, good to go.
But the runs consistently showed scatter in the final productivity. The core issue was uncontrolled evaporation and condensation during and after that SIP cycle. So instead of starting at, say, 10% media solids,
It would be different every time.
yeah, one day it might start at 12%, the next day, 10.5%.
Wait, a 2% increase in sugar or salt concentration before the culture even sees the light of day? That's a huge osmotic shift for the cells. The biological result is going to be all over the place.
Precisely. The starting chemical conditions shifted, but the blame was probably put on the culture or the media lot when it was a pure engineering problem, a boundary problem.
This brings us right to that first pillar then. Sterile boundary integrity. I mean, if the vessel interior gets steamed, Isn't the boundary clear? It's the vessel wall, period.
You'd think so, but it's not always that simple. The source defines this as a system property. It's not just the main shell of the tank.
So it's the whole path.
The entire path. The vessel interior, spargers, filters, valves, piping, all the accessory lines, right up to very explicitly defined isolation points. Sterility depends on that boundary being perfectly defined.
Okay, so where does this integrity usually break down in a physical sense?
Ambiguity in the definition is the philosophical breakdown, I guess. But physically, the highest risk weaknesses are almost always geometrical.
Things like dead legs.
Exactly. Dead legs, trapped volumes, thermally shielded valve cavities.
Okay, wait. When you say dead legs, for someone who hasn't been climbing around a massive facility recently, what does that actually look like in practice?
A dead leg is basically any piece of piping that extends off a main line but doesn't have any flow or has minimal steam contact. Usually it just ends at a sensor or a closed valve.
And if that pipe is too long?
If the pipe length is too long compared to its diameter, steam just can't reliably push the air out and sterilize the entire surface. So that tiny, forgotten pocket becomes a chronic reservoir for contaminants.
I can just picture it. A localized spot that hits, maybe 110 degrees Celsius instead of 121, and a spore load survives to wreck the run days later.
That's the risk. And the source material emphasizes that readiness requires 3 system-level disciplines to fight this.
Okay, what are they?
First, explicit boundary mapping. Documenting that boundary and making sure it aligns perfectly with the as-built condition of the plant, which, changes over time.
Right.
Second, cleanability and sterility coverage. Every single element must be demonstrably accessible to both clean in place and sterility. And third, drainability verification, making sure the boundary doesn't have these uncharacterized hold-up volumes.
That brings up that example of commodity biochemical production.
Mm-hmm.
The contamination was traced to these minor branches on manifolds. But isn't the incentive always to just run the existing piping until it fails?
It often is.
How do you sell management on a proactive, expensive piping redesign for drainability just because of a minor episodic issue?
Well, you sell it by showing the cost of what we talked about before, interpretability loss. The source points out that in those cases, the problem wasn't solved by just running a hotter SIP cycle.
Which costs energy and stresses the gaskets anyway.
Right. It required capital investment. A piping redesign for better geometry, better drainability, and dedicated steam contact. Readiness here means accepting that the hardware configuration itself can be the systematic flaw. So if defining the sterile boundary, pillar 1, is about knowing where the start line is, the second pillar, SIP execution quality, is all about making sure we execute that start flawlessly.
And sterilization in place is so often treated as just a binary pass-fail compliance step.
It is, but for fermentation, its quality is profoundly performance-defining.
It seems like everyone just focuses on hitting the temperature and holding it for the required time. Why isn't that enough?
Because lethality and, more importantly, reproducibility depend on 3 coupled mechanisms that go way beyond simple time at temperature.
Okay.
First is steam quality and distribution. We rely on saturated steam for efficient heat transfer. If your steam traps or regulators are failing, you get wet steam.
Which is just steam mixed with excess condensate.
Exactly. And wet steam dramatically reduces effective heat delivery and massively increases the risk of cold spots. The steam is basically condensing before it even gets a chance to sterilize the surface.
Which brings us to something I think we often overlook. Air removal.
This is so critically important. Air pockets are thermal insulators. Steam cannot penetrate a cushion of air.
So you get these sublethal microenvironments, even when the bulk temperature reading on the vessel wall looks totally fine.
Perfectly fine. So a proper SIP readiness plan has to include a defined venting and air displacement phase. You can't just assume pushing steam in will perfectly push the air out.
And then the third part of this,
continuous condensate management. Condensate pooling shields surfaces from the steam, which prevents sterilization. The source is clear. Equipment must be empty of liquid before you start SIP, unless it's explicitly necessary for some reason. You have to evaluate SIP as a hydrodynamic system.
This all leads directly to that huge industrial challenge. The cold spot. We know where they generally are. Near instrument ports, valve cavities, but the source says they aren't static. That's fascinating to me.
It's a central industrial reality. Cold spots evolve because components age. As gaskets compress, as seals degrade, insulation shifts from repeated thermal cycling, the heat transfer characteristics literally change.
So relying on the thermal mapping you did during commissioning 5 years ago is...
It's completely insufficient because the thermal effectiveness of the system is different now.
So thermal mapping is the key discipline here.
Yeah.
Mapping those worst-case locations.
Absolutely. And this requires multiple, specialized, calibrated thermocouples placed strategically at worst-case locations, not just the easy-to-read bulk points.
And we also have to consider what the source calls the second-order failure mode, just the gradual breakdown of materials.
Yeah, that repeated thermal cycling degrades elastomers and seals. It creates these microvoids that can actually shelter contaminants, even if the bulk cycle looks perfect.
Which means readiness demands proactive replacement of these fatigue-prone components. You can't wait for them to fail.
It's a total maintenance mindset shift. The pilot facility example shows this so clearly. They were getting episodic contaminations, even though the vessel wall reading was compliant.
And it was traced to condensate pooling in low-point drains and filter housings.
Yes. The fix wasn't turning up the heat. It was preventative maintenance on the steam traps and revising the drain sequencing to make sure air and condensate evacuation was actually complete. It's about performance, not just ticking a time box.
Okay, so let's say we manage to nail the sterile boundary and we perfect the SIP execution. What does all this mean for the measurements we rely on once the fermentation actually starts? We're on to pillar 3, instrumentation integrity.
Well, instrumentation integrity is just profoundly challenged because these sensors operate under extreme conditions.
They're getting hit with thermal shock during SIP, mechanical stress from agitation.
Constant chemical exposure from the broth, so drift, response lag, nonlinearity, these are not exceptions. They're common, and they have to be handled explicitly.
So we shouldn't trust the number on the screen just because we calibrated the sensor in a beaker an hour before the run started.
Not at all. Measurement accuracy isn't static. Take a pH probe. You calibrate it at ambient conditions and nice, clean buffers. But then the probe exhibits systematic bias once it's in the actual fermentation broth at temperature with high ionic strength.
The source called the matrix effects.
Yes, the chemistry of the soup itself changes how the sensor reacts. Or think about a dissolved oxygen sensor. It can start to respond non-linearly after it gets coated with protein, creating this apparent oxygen security that is completely inconsistent with what the cells are actually experiencing.
And these deviations, even if they're slight, they have direct cumulative metabolic consequences.
They absolutely do. A biased DO reading could drive excessive aeration, causing oxidative stress. Or it could mask true oxygen limitation, which triggers unwanted overflow metabolism, all while the reading on the screen looks perfectly fine.
So what are the readiness requirements for Instrum that go beyond that basic pre-run calibration?
The sources outline 3 key things. First, response time testing under actual operating conditions. Agitation, temperature. Is the sensor fast enough to see what's really happening?
Okay.
Second, drift, trending across multiple SIP cycles. You have to recognize that sensor aging is a predictable phenomenon, not a surprise failure. And third, routine cross-checks against independent measures, like off-gas trends, to detect bias before your control loops are materially altered.
Which flows perfectly into the 4th pillar, dynamic response reproducibility. Because a perfect sensor is useless if the system reacts to it poorly.
Precisely. This is all about the controls. Readiness isn't just about static conditions. It's about the system's ability to maintain those conditions. And that's compromised when control loops overshoot, oscillate, or lag.
So if the DO sensor is lagging and the controller is too aggressive...
You induce a massive chemical shift that the culture has to absorb.
Right.
That's the key link. In that high cell density fed batch example from the source, a slowly responding DO sensor, that's a pillar 3 issue, induces oscillatory controller behavior, a pillar 4 issue. The culture experiences these repeated, aggressive oxygen excursions that are totally invisible on average plots.
And that leads directly to more byproducts and more run-to-run variability.
Yes, true readiness means tuning your controllers to the performance limits of your aged, real-world hardware, not just the theoretical specs from a manual. So let's try and synthesize this. Fermenter readiness, when you look at it through this engineering lens, is really about the systematic elimination of latent environmental uncertainty.
Or at least tightly bounding it across the physical hardware and the measurement integrity.
Exactly. And since microbial systems amplify even small deviations in a nonlinear way, incomplete readiness adds these dangerous, unintentional fluctuations on top of the inherent scale gradients that already exist in large vessels.
Which results in the most costly outcome of all. interpretability loss.
Yes. When a run underperforms, but there are no obvious alarms, no contamination signals, the deviations get misattributed to the easiest scapegoats.
Strain instability, a bad seed train, media recipe sensitivity.
All the usual suspects. But the underlying driver is actually facility-mediated variability. Readiness defines the engineering envelope within which your biology can be meaningfully, and more importantly, reproducibly expressed.
That is such a critical takeaway. It shifts the burden of variability from the R&D lab back to operations and engineering where it often belongs. So, based on the source material, where are the big unresolved gaps in the industry right now?
The sources identify 3 specific challenges. First, we still lack reliable methods to predict where cold spots will form as components age and drift over time. We know they shift, but we can't really model it yet.
Okay, what's the second?
Second, we need to establish universally robust criteria for what constitutes representative sensor placement, especially in massive tanks with huge scale-dependent gradients. Where is the one true spot to measure DO when the fluid dynamics are so complex?
And the third, I assume, connects back to that instrumentation pillar.
It does. It's about how we can effectively integrate sensor aging and drift models into our routine readiness qualification. We need to stop treating drift as a random exception. We should be using machine data to predict when a sensor will fail to meet its performance requirement, not just wait for it to happen.
That really reinforces the central message here. Readiness has to evolve. It can't be a simple one-time release milestone. It has to become a measurable, continuously defended operating state.
It's that deep coupling of sterility engineering and instrument lifecycle management. It's not just good practice, it's the fundamental key to achieving robust industrial scale-up and getting predictable biological results run after run.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.